Number 7. Okay. Number 7. My guess is A, B, and C, parts A, B, and C weren't bad. Like the more crowded they are, the higher electric potential. If there's a big difference in crowdedness, then there's a strong desire, a large electric potential difference. And figuring out which way they're going to go, they're going from crowded to not crowded. Okay. Part D, though, that's the challenging part. So the equation you're looking at is this. You're looking for the amount of energy transferred over the charge transferred. So arranging that, bringing the charge over, we want to know what's going to cause the most amount of energy for part D. Okay. So for this one, they're really motivated. They're really crammed together. They're going to go from here to here, but this isn't going to be that big of a shock because there weren't that many electrons on here in the first place to make the jump. It's a limited number. Okay, this is a great pictorial representation of the Van de Graaff generator. This guy right here would be representing the Van de Graaff generator. This would represent me. Okay, this is why I didn't get harmed, destroyed. They're super packed together, but they're just not that many to make the jump. It's a limited number. Versus the outlet, it's huge and expansive, but they're not that close together. Okay. This one, they're big difference in electric potential, so they're super crowded, not so crowded. They're going to jump, and there's got a lot of room for these guys to come over, so that's going to be a big shock. Okay, there's a lot of electrons that can make that, and it's a high electric potential. Here, it's still a high electric potential, but the number of electrons jumping from here to here until these are equally crowded will be not that much because there's not that much room to jump into, if that makes sense. Just like, oh, we're filled up. And then this one's, what I tried to show you was a high electric potential and then like a medium electric potential. So there are not going to be that many that actually make the jump. I recognize this is fuzzy, like there's no math numeric values. You're just kind of like, On the test, it's going to be an apparent, like there'll be one question with this. Okay, so, and that'll be, if you understand this conversation, you'll be fine on that question. Andrew.
So for this, like, size doesn't like really matter for like the third one, because I put weight just because I assume that's, yes, there's a lower density, however, it's just not many electrons that be able to travel, like pass through. So you just assume that this just has a lower density that would still be strong.
Yeah. Yep. Good with that? Okay. Um, all right, I'm gonna do this. All right. So, question for you. Nope, not that question. Yep, you've already answered that question. There, that question. Okay. Okay. Your car is a safe place. Okay, it is a safe place. Now, let's say you take your 4 tires, you stack them up like pancakes into a middle of a field as a thunderstorm rolls in, and wave to the thunderstorm. Ah, you can't get me. JP. No rims. Like the metal part. Okay, so here's the reality. Air is a pretty good insulator. It just traveled through miles of air. You think your little stack of tires, rubber tires, is going to protect you? It just looks at that and goes, like, you are dead. Like, there is no hope for you. You're dead. I will. Yeah, no, I'm gonna protect you. No, it went through miles of insulation. Okay, here's why you're safe in a car, because the frame is made out of metal. Okay, where does charge reside? Where does if a conductor is charged, where does the charge go on a metal, on a conductor? To the outside. It goes the outside. So the charge, rather than going through the interior, goes around the outside. Notice, JP, here's your answer. The lightning bolt going right through the rubber tire. Okay? It's not the rubber that protects you, it's the metal frame. So even if your car has a fiberglass body, it still has a metal frame. Okay? The electric field inside the conductor is 0. This is called shielding or Faraday's cage. Okay. Yep. There might be some problems it would have afterwards, but you would be totally fine. You might feel weird. You might be deaf from the thunder. But probably. I mean, your ears would ring. Okay. So this is the world's biggest Van de Graaff generator. This is in Boston. I don't know. It's a lot. So like this is like a 6-foot arc. Okay, this would put you on your butt, probably knock you out. But this guy in the metal cage is safe. Okay, because the charge goes on the outside. Some more practical applications of this. So coaxial cable. I don't know if you ever heard of coax, like any type of thing where you're sending a signal that you don't want interference with, has this wire mesh around it. This is just providing the conductive shell to protect what's in the signal. This is another example of coaxial cable. This mesh doesn't do anything except protect the signal from any type of like electric fields or interference or stuff. The inside cavity of electric guitars are lined with metal for the same reason, protect it from any outside interference. Receiving like components or like computer components, electric, whatever things in the mail, they ship it in this plastic, metallic packaging, which is anti-static, which protects like the electric field inside here is 0, protects it from all things on the outside. Okay, so this is the same Van de Graaff generator. This is a Tesla coil. This isn't static electricity, but it does shoot bolts of lightning. And this guy would be in a lot of trouble, except that he's standing in a metal cage. Isaiah. I do, not even close to that big.
Is it easy to build one?
No, it is not easy to build one.
How much do they cost?
The materials, I'm guessing, is definitely in the thousands. Okay.
So let's say he's standing in that cage and his arm just like brushes the metal. Does he get zapped?
Great question. No. So this guy, the show, I've been to the show. He touches the cage during the show, and it shocks, and he's fine. Now, would he be zapped if he stuck his finger outside the cage? Yes, I think that would be problematic. But so long as he's on the interior. Yeah, but it goes to the ground.
I understand it goes like, but like violent zapping it if he just touches like the side of the cage.
Yeah, the electrons would rather go to the ground than go to him through him, if that makes sense. And you're on the inside of it. Anytime you're on the inside of a conductor, the electric field is zero. So there's no motivation, there's no force to say go in. It's always on the edges. Yep. Okay.
You can almost feel the tension. I'm being hit by lightning. My hands are buzzing. Hey! Oh, now it's doing stuff from the car. I've got error up on the dashboard. Handbrake light flashing.
But he's not dead.
Yeah, my car would just like, yeah, my car would not last. You should try. Yeah. No, honestly,
what are planes made out of? Metal.
Oh, yeah, what would it do to a car that's already almost broken?
Fix it.
They could fix my engine.
Okay. So, if you were in that plane, you would be fine. You'd probably have to change your underwear. But other than that, you'd be fine. Okay? Plane's fine. It's made out of metal. It just goes around. It keeps on going to the ground. JP.
So, on that plane, why did it go through it instead of just to the ground? Like, why didn't it,
Go through the cavity of the plane?
Like, yeah, no, why did it, like, hit the plane? Why didn't it just go straight to the ground?
Oh, it just happened to be in the path of the step leader as it was going down. I mean, it doesn't happen all the time, but it definitely happens. Yeah. So, thunder, just real quick. Here's where thunder comes from. The lightning bolt's super hot, and it causes the air molecules around that to expand. And then when the lightning is gone, you've got this hole or this low pressure, and so the air comes back, crashing back, and that's the thunder. That's where thunder comes from. Okay, Maddox.
Are the electronics of the plane like affected by lightning?
I'm pretty sure they've designed it in such a way that it wouldn't be.
But if it was a car, it would be.
I mean, with that, so the guy being shocked, the that was like a continual bolt, like it was fabricated. Like lightning is more like.
Okay, so
I think it'd be all right. Electric car is still be fine. Okay, so these guys are standing on Tesla coils, but they're wearing chainmail. Okay, good with that. All right. Did I show you St. Elmo's fire? I think I did with the finger. Okay. Okay. Now we've got some demos. Which are gonna be good. All right. So first off, first question: why do I stand on the styrofoam blocks? Why do I? Oh, let's see. This is problematic. It's not even bright enough to show my. Oh, there it is. Okay. Why do I stand on the styrofoam blocks? It is an insulator. What would happen if I didn't stand on the styrofoam blocks? Yeah. But not with the lights off. Okay, watch my shoes. See that? Okay, good with that. So, what is that? What is that doing? Because why they're going on the floor? Okay. So standing on the foam separates me, isolates me from the ground. That makes sense? Okay. This next part here, it's a really cool demonstration. What this involves everybody if you'd like to participate. Okay. I need someone to stand up here. What do I do? You stand out here, leave your hand on there. And I need everybody else who wants to have fun. Stand over here. CJ, come here. Isaiah, come here. What you're going to do is you're going to take your right hand, put it on the person's right shoulder in front of you. Okay? If you have a pacemaker, I would not suggest participating. Okay. What? Just get in a line, single file line. Quickly. Okay. So the question is okay, so the question is who's gonna feel it the best? Isaiah or Rachel? Or is it all gonna be the same? Okay, so when I say, here's what's gonna happen. When I say, well, I turn it on, I'll say 3, 2, 1. When I say go, you guys fist bump. Just quickly, just keep your arms down though. Keep your arms down until I say that, though. Okay?
Yeah, am I gonna feel it?
How much is this gonna hurt?
Yeah, you'll feel it.
Oh.
On your marks. 3, 2, 1, go. Okay. Yes, yes. All right. Isaiah, did you feel it? Rachel, did you feel it? What? Where did it stop? Who? Okay. Why did the effect diminish as it went down? There's a little bit of that. There's going from you to the ground. That's a little bit, but there's other things. If you're all wearing shoes, which you all are, that kind of prevents you from grounding. Why is it getting less as it goes down? Sort of. It's not like you're retaining it. It's just getting more and more diluted. The concentration is super packed, but as it goes out, they're spreading out more and more because there's more area to spread out. Does that make sense? All right, mix it up.
What happens? What happens if we